old design of kindelia and the current one is that the old one was very closely related to the HVM. And it had global rewrite rules that you could install on the network, and it had like all sorts of rewrite rules. And it had a large memory of 128 bits, which was different from the main HVM version, and because of that, it needed to be maintained independently, and it had a memory rollback mechanism that allowed for some good things. But the problem is the HVM right now, it has like the actual implementation of the HVM, it has two problems that make it not ideal for a blockchain. The first problem is that you can construct a program that will cause memory to leak on the HVM, because since it does not have the uplinks on the lambdas, which is an optimization that makes it faster. But because of that, you can construct some programs that are not very common in practice. So it's not really a problem for like a practical runtime like the HVM, because you can like have a global garbage collector that runs like very rarely, because like it's not something that most normal programs have. But the problem is on the kindelia network, you can still construct those programs. So you can make a program that will leak memory. And if you do that, you can flood the memory of the network with a lot of garbage. And that was a not solved problem. So we could not release a mainnet because of that problem. The second problem is the problem of parallelism. The old version, in the same way that the HVM works, it used a lazy evaluator for the interaction nets. And that lazy evaluator, it's good because it does not do any wasted work, but it's bad because you can't measure the amount of parallelism that a program has before running it. So after you run it. So because of that, you cannot tell when a program will be very parallel or when a program will be very sequential. And because of that, we cannot make the gas table the costs of the blockchain, assuming that programs will be parallel, because an attacker can construct programs that are sequential, and like he can flood the network with sequential programs. So like the whole parallelism like is good, but it does not make any difference because we need to assume the worst case, that is all programs will run sequentially. Okay, so they will not run like that's not the case. Like not all programs will run sequentially, but we need to assume the worst case because that's what an attacker would do. An attacker would construct always the worst case. So, and because of that, there are some minor changes that I'm making to the design of the kindelia. Instead of using like global rewrite rules, I want to use interaction nets. Okay, so we have those uplinks, so that solves the garbage collection issue. Um, and finally, like also interaction nets also allow us to measure the parallelism. So that's a problem that use interaction nets instead of the interaction calculus thing that HVM uses solves. So that's the first change. And the second change is, I think that's the old Kindelia project, and that was the main problem. Like, um, it was like I was not working on it. So I asked someone else to do it, and the code started to grow and grow and grow. And like kind of the person that was working on it started losing a lot of productivity because the code was so big. So that person could not do big refactors anymore because there was just so much code for him to maintain. So that's a normal problem, like something that less experienced developers usually happen with them. Like they lose the control of the code because it grows so big. So because of that, like because of the state of the code, even if we wanted to keep the old way, like the HVM way, we would probably want to refactor it and rebuild it anyway, so we don't lose control of the code. And like since we are rewriting things, and like since there are like were those problems, I also used that opportunity to make like a few small changes on the protocol that solves the issues that we had that did not allow us to create a mainnet, even if the code was good. So in short, like um, to sum up everything that I said, first, the code was too big, so we will need to refactor it anyway because we lost control of the code. And even if it was not um, the case, the design itself of the network had some minor issues that would not allow us to create a mainnet. And to solve those issues, we are going to use interaction nets as the computational language instead of the interaction calculus that the ATVM is based on. Okay. And finally, we have two options here now. Okay. We can use full interaction nets or we can use interaction combinators. And I'm strongly opposed to using full interaction nets because, especially for kindelia, okay, because interaction combinators are much simpler, and we want to keep the protocol as simple as possible. Okay, that's very important. First, because that makes it easier for us to create and maintain and ship. Okay, we want to have the ability to ship, so it increases the chances of success. So we want to keep things simple. And second, it makes it easier for people to create clients, okay, or for us to create new clients in other language. And it's important for a blockchain to have client diversity, okay.
Really?
So for those two reasons, wait, I want to use interaction combinators instead of interaction nets, okay.
Using interaction combinators would make like building new clients would be easier.
Yes, no, just like everything that makes the code smaller makes it easier to build new clients.
Oh,
And
okay.
for sure,
I
like
see.
using interaction combinators will have way less code than using full interaction nets.
Okay.
Okay? It's like it's 100 lines of code for a full implementation of interaction combinators. So again, some other changes, like small changes that we want to make is we don't want to have like these global heap that we do rollbacks anymore. So we have a simpler construction that's just like you run the contract and the contract returns an update of the state, and the state itself is just a tree. So instead of being like, because before the state could be any interaction net. So you could have lists, you could have trees, you could have lambdas, you could have anything on the state. And I don't want to do that anymore. It was better, okay? It was better in the sense that it was more efficient. It was better for the network, but the complexity was also bigger. So I like in this take, I'm going all in the simplicity. Okay, I want to keep things as simple as possible, and sometimes I'm sacrificing a little bit of performance, a little bit of expressivity for the sake of simplicity. And I think we should do that. We can always extend the network later, but for the first version, let's make it as simple as possible. Simple, minimal, clean, and let's ship it. Okay, that's the most important thing. Okay.
Okay. Quick question. You said like that implementing interaction coordinator is like 100 lines of code. How would be like full interaction nets? Just so I have an idea.
Not much more, but like 300 if you are very like small in the code, but you need to have a table of rules. You have to have a parser for rules. You have to deal with all those rewrite rules instead of just two, and you need to go through the table and like it's more complex. Okay, it's perhaps like 3 4 5 times more complex, and like it's kind of like comparing implementing um the lambda calculus with algebraic data types and pattern matching versus implementing sky combinators. Okay, sky combinators is like 5 lines of code, and like implementing the full lambda calculus with data types is like 500, like 1,000. So it's another level. It's not like, oh, it's a compiler level complex. No, but it's
Mhm.
relatively more complex.
Okay.
By the way, Henke, if you want, and check out my IVM repository, which is basically implementation of full interaction nets.
Mm-hmm.
You could probably, I mean, if you remove all the comments, it would be shorter, but then it would also be harder to understand. But this is kind of like a minimal implementation. But
Mm-hmm.
yeah, I also agree it makes more sense to just use interaction combinators.
Okay.
Also, yeah, I also agree it makes more sense for the first version to focus on simplicity and launch it at least as a testnet, and then iteratively add features if we are if we want more, or if we are not yet competitive enough or something like that.
Okay.
How would the performance between interaction combinators or interaction nets be? Like the difference between each.
Sorry, can you repeat the question?
What is the difference between the performance of interaction nets and the symmetric interaction combinators?
So the thing is, Oliver managed to implement like the full interaction net system, and it was like as fast as, perhaps sometimes faster than the HVM in normal computations. So that was good. That was really good. But the thing is, interaction nets are actually not slow like the interaction combinator. Sorry, they're not slow. And a curious fact is that the implementation of interaction combinators on that that repository, like that's very simple, 100 lines of code, it's actually performing like 3 times more rewrites per second than the HVM. Like it's actually 3 times faster than the HVM. So why it's actually slower? The problem is it is doing more rewrites per second. But if you want to do a normal computation, like I want to sort a list, I want to like do something with normal data types, you need to lambda encode everything. And when you do that, every time you call a recursive function, you need to allocate the whole body. And first, that's a lot of wasted like allocations. And second, it takes way more rewrites. So like it does more rewrites per second, but it takes 10, 20 times more rewrites. So that's a problem. But the thing is, that can be avoided, okay? Like you can start with interaction combinators and you can avoid those extra rewrites for normal programs using some other optimizations that I did not explore yet. So I'm very optimistic that if you just like stick with interaction combinators and research those other optimizations that allow us to avoid those like that constant slowdown because of more rewrites, and we will be able to achieve the same performance of the HVM using interaction combinators. And again, today, if you like have a Lambda calculus program, like this repository will be faster than the HVM because it's better at dealing with lambdas. The only problem is again that since you have to lambda encode everything, you have an overhead that you lose performance. But that overhead, I believe, we can cut it out without going in the direction of having global rewrite rules. That's basically what the HVM is. Like it's the lambdas plus global rewrite rules to optimize those programs that would be slow if you lambda encoded them. But I think we can find other ways to solve that some problem that don't involve global rewrite rules. Okay, that's the idea of the HVM. And again, or like global interaction combinator rules. Okay, perhaps I'm wrong, and those global interaction combinator rules are the best and only way to have normal programs running as fast as the HVM. But I don't think that's the case. There's no reason to think that's the case, and that's probably a very easy problem to solve. It's just that the HVM was the first time we managed to solve it.
Okay.
Okay. So what's the plan? What are the next steps? I need you guys to have initiative. I need you to have leadership and make things happen. So can I help with anything else? Any other question?
So should we use any of the old code base of kindelia, or should we get familiar with the old code base in some way? Or should we start from scratch?
Just ignore it. There's nothing there that we want
Okay.
to. Just like the Renash is already. By the way, did everyone get the message that I sent? The message about like the change of leadership. I did not send it to everyone. Did you?
No.
You don't send to me and Sab.
Okay, I actually did not send to anyone other than the Renash and Cypher, and I expected them to send to other people, but I did not ask, so I like that was stupid from my part. Sorry. So
No problem.
I will okay, I will send in the chat right now. Okay, so you can read it now, you can read it later, but in short, um, we'll be passing the leadership of the kindelia project to Oliver. Okay, I still did not talk with like everyone about this. I even talked with Henke about the possibility of him taking this leadership role, but since he decided that he does not, it's not his favorite thing, and he does not can't guarantee that he'll be working on this on the long term. I think it will be safer for the company to let Oliver take this role and have like Hanky and everyone else here working on the Kindelia project, okay, under his leadership. So that's the idea. Like he'll be the one leading this implementation, and the goal of this team will be to again and ship the client of Kindelia with the new design that that they can launch on the terminal and that will connect to peers and that I can make transactions and all those things and like deploy contracts that will be running and use interaction combinators. Okay, so that's the goal to release the new client of Kindelia. Okay, and again, guys, I really think that this will be very simple. Okay, um, I know that like this sounds like perhaps like a big scary project, but like it's truly very simple. Like you just like and the whole thing like I actually believe that the whole thing will be like 1,000 lines of code or less. Like you just need like the interaction combinators for the computations. You need a mechanism to store contracts like accounts and signatures and transactions and balances and the state of each contract. So you need that. And then you need the connectivity that we don't have. We don't know how to do. But I don't think that's a big problem because we probably want to use something that's already done. And there are billions of things. Like there's lib peer-to-peer, there's like Celestia. There are many ways to do the networking today without needing to like write a whole protocol from scratch. And even if you needed to do that, it's actually not that complex like to write a peer-to-peer protocol nowadays. We have so many resources. So, but again, the most important thing is for the thing to be simple and to work. Like we want it to work, we want it to be stable, we want like to trust that it does not have bugs and problems. Again, that's the main reason we are making this protocol even simpler without the problems that we had before with all those complex rewrite rules. So I actually think it will be really simple. And once the client is released, that let's say this is the first goal, okay? Once the client is released, I think everyone here should be working in the infrastructure. So in a wallet, in a browser, integrating with MetaMask. There is so much to do, like community, dApps. So like there is just so much to do. I don't think that there will be a lack of things to do. I think just like the main challenge is to get the client working. Okay, once the client working, I think everything else will run smoothly, and I'm very optimistic about that. And I'm very confident that you guys like are over capacitated to do that. Okay, you all together, you have way like more than what's necessary to ship this product, this project. Okay, so I'm very confident that you'll be able to do it under the leadership of Oliver.
Okay, nice. I have a question because it's not so clear in my mind how, like, the general architecture of the client. We said to use. We're planning to use like the interaction combinators, but will we use a language that runs on interaction combinators, or will we code it in Rust and then use interaction combinators for what? For the execution of smart contracts? For I'm not so clear on the general architecture of the program. Okay.
Can you see my screen?
Yeah, I'm seeing.
So blockchains, they need a model of computation. Okay. In the case of Ethereum, in the beginning of Ethereum, let me record this. Okay. So in the beginning of Ethereum, Vitalik wanted to to use a register machine, okay? A register machine, it's a model of computation for Ethereum, okay? And some people, like I believe Gavin, or like, I don't know, someone else, told Vitalik that this is not a good idea for several reasons. So instead, the Ethereum use a stack machine, okay? So the EVM is based on a stack machine. What that means? It means that the main model of computation is like a Turing machine, but it's based on a stack. So you have like opcodes like push, pop.
It's like
Sorry?
it's like the Java VM.
I don't remember if the Java VM is a stack machine. I don't remember. But the thing is, you have like those operations that mutate a stack. That's like the main state of the execution of the program. So like you have a stack and you can push data to the stack and you can pop data to the stack and you can duplicate data on the stack. And like that's pretty much how your program works. But the ATVM also has some opcodes that work kind of like a register machine. So like it can access memory, it can access the disk. So like you have mstore, you have mload, you have store and sload. This saves data to a memory. This saves data to the memory is just something that you can use to do computations during the execution of the contract. But when the contract stops, like when the program returns, the memory is cleared, while the store is a permanent storage. So whenever you use that, that will persist for the next calls of the contract. So again, the Ethereum uses a stack machine. I believe that Cardano is based on the Lambda calculus, so it has like this Plutus language that's kind of like a Lambda calculus like language that's executed by the network. Not sure how they protect against the DOS of like beta reductions. I'm not sure if beta reduction is up code here, but if it is, it's a problem because it's hard to quantify the cost of a beta reduction. But again, I don't know much about Cardano, so I could be wrong about that. But you need a way to run programs, okay? So Ethereum uses a stack machine. The difference is that Kindelia will use interaction combinators, okay? So interaction combinators replaces the stack machine. So instead of a stack machine, we have interaction combinators. So that's how we do computations. Yes.
Can I interrupt you, or you prefer to?
Sure, go ahead.
Those VMs, they only, like, from what I understood, like we have the client code, which is a beast, a thing, and we have those VMs that are only used to run smart contracts, or are they used for something else as well?
You're asking if like Ethereum is only used to run smart contracts or
The stack machine, the VMs.
I don't get the question. You're asking if the stack machine is used only for blockchains?
No, for running smart contracts, for the execution. That
You're
code.
asking if the stack machine is used only to run smart contracts or if there's something else that they do with
Yeah.
that?
Yes.
Yeah, like on Ethereum, like the stack machine is your only called when you call a contract. So the stack machine like is created, instantiated, and then a lot of things happen. So yes, it's like as far as I know, it's only invoked when you call a contract, and that's like the execution of a contract.
Okay.
So again, on Ethereum, you have like contracts that have a code, and the code of the contract is the stack machine instructions. Let me say like instructions. Okay, so that's the code. So like you have like instructions like dup, store, add, sub. Okay, so this is a list of instructions that they encode to binary. So like dup becomes this. This is just an example. Okay, this is not correct. So they encode the instructions, like the code of the contract to binary. They concatenate, so you get like a buffer with the code of the contract, and then this is stored on the contract in the blockchain. So balance Okay, so the state of the Ethereum network is a map of contracts. There is also accounts that have an address, don't have a code, but have a balance. And there is also other things like the logs, and that's not useful. There are some receipts, things that I don't understand very well. There's the contract also has a state. So it's pretty much a tree. It's pretty much it's like a hash map of U 256 to watch. It's easier to do that way. Okay, so like this is the state of the Ethereum network. There are many things here. So on the Kindelia network, we have contracts, the same thing that has an address, same thing, no, not different, and it has a balance, probably same thing, perhaps 64. Not sure if we need so much bits. It also has a state root, but it's slightly different because it's just a tree, binary tree. And like the main difference is that the code, instead of being like the binary of a lot of instructions, dup, add, blah, 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 it's the binary encoding of interaction net. So like on Ethereum, the code corresponds to an assembly thing, like dup, move, add, and store, etc. This is the code of an Ethereum contract. And on Kindelia, the main difference is that the code is the binary serialization of some interaction combinator net. And instead of the root being like the first index, the root is like the free port of this network. It's always a network with a single free port. So that's pretty much like just an example. Okay, it's very ugly drawing, but it's just an example of an interaction net. So yeah, so that's pretty much like and like on the Kindelia network, we have like this. So the network, like we can split it in three parts. I would say that's like three big parts in the sense of lines of code. Okay, I can split in three parts that have a lot of lines of code. So the first part is the interaction combinator. Okay, the interpreter of like the interaction combinators. That again is 100 lines of code. Again, could be a little bit bigger, add the numbers or something like that, but it's very small. But like it's one of the components. The second component, I'll call it the global network state. Let me inside this, like he writes.
And on this new design, the cost will have the like the worst case scenario where we will execute everything sequentially, or will we know the cost beforehand, even when it's parallel?
Oh, look, we will have like this implementation. It will have two things that will come out of it in the sense of cost. The first thing is the number of writes, and they probably actually want to separate like annihilations and commutations, because the gas cost will probably be different, like one for this and two gas for this. So in the end, you'll have a gas. Okay, that's the sum of the annihilations added to 2 times the sums of the commutation rules that you need to run. And we have a parallelism degree that will be a number from 0 to like something that will be a constant, I believe. For example, 16. that will tell us how much parallel this program was. And that can be measured, and Oliver can explain this better, but that can be measured because we'll be using an eager evaluation model. Okay, so instead of walking through the tree lazily, we will have all the redexes that can be reduced in parallel in a buffer, and then we'll reduce all them in parallel, and after that we can have an idea of how parallel this program was. So we can deduct the cost. So for example, the cost was like 1,000 gas, and the parallelism degree was 4. We actually only charge this amount of gas of the user. Okay, so gas deductions.
That's one of the reasons for the redesign, because beforehand we didn't know about that. We didn't know this cost, right?
Yes, because the optimization that the HVM uses to save memory in the lambda and the application case, that instead of using 3 pointers, we need only 2 pointers on the HVM. So we save like a third of the memory, but this is not, this does not change, like this does not interfere meaningfully with normal programs. So it's a good optimization in normal programs, but it does not allow us to reduce in the eager reduction strategy that's necessary to compute the degree of parallelism. So yes, we want to have those pointers. We can't omit them. Okay.
Okay.
Yeah. So yeah. So the first component is the interaction combinatorial interpreter. I'll say that, and if we add the parallelism degree and the costs and other things, let's say this has like, and perhaps a parser and other things. Look, it has 500 lines of code. Okay, that's the maximum. Like the parser will probably like half of this complexity, so it's not very complex. So the global network state is like where we store contracts and the transaction rules of the. Okay, I'll just say that this is the global network state. So contracts, address, balance, code, and address, balance, code, and there is also the state, of course. We will be merging, okay, contracts and accounts will be the same thing to keep it simple. And the transaction function. Deploy call contract, okay, and send money. So, so we have an initial state, we have a contract with like address, balance, code, and the state of the contract, and we have a transaction function. This is where we implement what a transaction is, okay? So we'll probably have like just a single transaction that, and again, the Renash can explain better the design that I made, but we have this like this file. Let's say that this has like this amount of lines of code. It's just how much I expect. So it like explains what a contract is, what an address is. The signature is also here. So like if it includes the signature, it's a little bit bigger, but it's also very simple code, nothing new, nothing complex. Okay, let me include this here. Because again, signatures are part of transactions, so that's why I'm including the crypto stuff here. And finally, we have the, I'll say, the peer-to-peer networking. That's the nodes, like the actual process of the node. It's the messages that you the block propagation and the database. And the consensus, of course, like the consensus algorithm is here. So like the hash function, like they pretty much the same thing as Bitcoin. Like you send a transaction, and you have a pool of transactions. You include that in a block, and you propagate the block, and you have like peers, and you connect to them, and you handshake, and you have a database of blocks. And this like it is actually very complex, but it's not complex because the point is this is where you use libraries. Okay, so So like, we don't want to do a lot here. We want to use things that already exist. So like lib peer-to-peer, and even like products like Celestia, we can find the things that take care of this, because this is shared across all blockchains. So all blockchains that exist need the same kind of mechanism. So this is not exclusive to us, and we'll of course like surely be able to find projects, open source projects that have a lot of code that we can just use. So the main challenge of here is finding the right libraries to use. So like, if you just spend a lot of time researching and looking at all the projects and blah blah blah, we will probably find something that does all of this to us, and we don't need to do. So those three things together are the network. So in short, the usability of Kindelia. We launch the client. So for example, Kindelia start.
Again, a quick question before you proceed. Which consensus algorithm will be using?
So we want to use a proof of stake algorithm if possible, because that's what some of the investors want us to use. If that's not possible, we'll just use proof of work. But again, it depends on what libraries we find, and the easiest, like, let's find the root of less friction. Okay, I don't have strong opinions about the consensus algorithm. I just want something that works and that can't be attacked and exploited. So, and I think that Aaron can help us also make this decision, because like, he likes proof of stake and he has more experience than myself about this. So yeah, I don't know, but let's favor proof of stake if possible.
Okay.
Okay. So the usability, we do kindelia start. So it will start connecting to peers. And connect to peers. And then we can make a transaction. So for example, Kindelia transact file.kdl, KDL. The file.kdl can be something like this. So we can deploy a contract and we can call a contract. Of course, like, this is all like encoded like to binary, and like you have this transaction, send this transaction to the network, and then like we probably want to have some kind of like Kindelia scan.org, something like that, like scan.kindelia.org, where we can like look at those contracts that are deployed and their states and the state of like an account and things like that. So very, very similar to Ethereum. Okay, very simple usability. I think there is nothing much new on Kindelia. It's basically like the same concept of Ethereum. You just want to use a different VM, okay, a VM that's based on interaction nets that can be made parallel and things like that. Okay, so that's pretty much it.
Do we have
And
formal proofs on Kindelia?
It's not related to Kindelia. The thing is, Kindelia uses interaction nets as the model of computation, which means that it's very efficient to compile a functional language to Kindelia, which means that you can take Agda, Coq, kindlang, and compile to Kindelia in the future, okay?
Okay.
But it's important to understand that Kindelia is good for formal proofs because it has a model of computation that's less expensive than stack machines to run lambdas, okay? But it does not have any kind of internal formal proof thing. It's a completely separate thing, okay?
Okay.
And for these transactions, we can also just send money from one account to another without invoking a contract.
Yeah, same thing as Ethereum. This is something that Anastasia can explain. I sent him a very poor specification of the network that also has some problems because I forgot that contracts need to send money to other contracts. But like other than that, it's a very complete specification. So I believe he'll be able to explain it better.
Yeah. Let me just get some water.
Okay. So stop streaming. Do you have any question for me?
You're asking for everybody, right?
Yeah.
I remember like seeing a long time ago. Like I'm not so into the crypto world, so that may be a noob question, but I saw somewhere like on kindelia a few months ago. I don't know how long ago that kindelia will be a peer-to-peer crypto computer that it's tokenless. What do you mean by that? And will we be also tokenless in this new design?
No, it's not tokenless. It's simple. It has a token. It actually simplifies the implementation to have a token because without a token, you need to have a more complex mechanism that allows people to deploy contracts that are tokens, and any token can be used to pay miners. And people got confused with that, so it was hard to implement. And it was better, I think, but not for the marketing, because for the marketing perspective, it just made people confused. So like, why do we want to implement something that is more complex, will make people confused, and will make investors less prone to invest because now they think that another token can overthrow the token on that they are investing on. So like I believe it was a net negative. It did not even make the code simpler. So let's just screw that idea. Let's leave it as in the realm of ideas and have a token in the actual network. I forgot to talk about this, but again, it was a minor aspect of the network. It was just a polish that people made a big fuss about and was like, okay, like it was not supposed to be such a big deal. So let's just not have that, okay?
Okay.
So let's just have a token, and the token can be like KG, something like that.
I remember.
Savio, great question. The reason that we are not using the ATVM is that again, ATVM is very complex and it's not 100% future-proof. ATVM has like those rewrite rules, and we actually want to get rid of them and have a better version of the ATVM in the version 2.0. So like we want to have like a better version of the ATVM that does not have all those rewrite rules. So I think it would be a mistake to commit to the way that the ATVM is done because you don't know if it's the best way to do things. So it's not like it's great, but it's not future-proof. It's not like so natural that we know that it will never going to change. It can change. It can get better. And getting better is changing. But we don't want things to change on that blockchain because a blockchain is that. Like the first version can be the last version. So the good thing is that when we make it to use interaction combinators, it can change. Like interaction combinators are like timeless. They are like very future proof. There is nothing to change. Like it's just two kinds of nodes and two kinds of rewrite rules. And those are the fundamental rewrite rules of computation. That's the ability to erase data, the ability to copy data, and the ability to communicate. So communication, erasure of data, and duplication of data. Those are like the core rules of computation. So it's never going to change. Like if it changed like how interaction combinators are, we pretty much need to change like how computers work. That does not make any sense. So in short, like interaction combinators are very future proof, and that's why we want to stick to them. Okay, it's way less likely that they will need to change in the future than anything else we could do. Okay, so we want to use just interaction combinators instead of the full ATVM. Oh, of course, like there is also those problems, but again, I'm like, if you solved those problems on the ATVM, there would be still this problem of like it's not as future proof because it can change a lot.
I remembered something else about when I read kindelia months ago. It was a difference between Ethereum and kindelia. One used Ethereum used the Merkle tree that stores the transaction something, and we found a way to make that more optimized. Is that correct? Am I
Sorry, what more optimized? Can you say this in
Yeah,
Portuguese? Perhaps
I
I
don't exactly remember. That's also why I'm asking.
had some trouble understanding what you said.
Yeah, it's something about a data structure that on Ethereum it's a tree. I think it's the Merkle tree.
Yeah, it says
And
it replaces expensive Merkle tree insertions by reversible heap snapshots,
yes, this
greatly
will give
reducing the
this
cost of
reversible
S-store and
snapshot.
S-load.
Okay, that deserves some explanation. So let me talk about this. In the past, like the first version of the Kindelia, it had something that was very cool. That was um, when you run a contract. Let me explain. I have to explain that in English, but okay, I can do that. So when you run a contract on Ethereum, let me talk about Ethereum. What happens is the contract has like this sequence of like instructions, the um, store, mload, add, move, store, move, load. So suppose that this is the code of some Ethereum contract, okay? So what happens on Ethereum is that when you call the contract, it starts reading line by line. So it opens the contract and it reads this line, and it will affect this. It will create a new stack when it begins, and it will like start adding things to the stack. Okay, so it reads this line, and then this, and then this, and all those lines, like those lines here, they are just doing like temporary computations, like they're dealing with memory. So they're adding numbers, they're multiplying numbers, they're doing things that are temporary. But this instruction, a store, it's different because when you use this instruction, instead of dealing with the local temporary data, this instruction, it will actually make a change in the global network state. So let me draw a globe here. So this is the planet Earth. It's a very beautiful drawing of the planet Earth. And that's the state, like this Brazil. And that's like,
Oh my god.
so like when you use the store operation, it will change the state of a memory slot in like the memory on the persistent global memory of many nodes around the world. Okay, so this is permanent, this is persistent. But the thing is, the problem is, suppose that you have some kind of list, like one, no, not a list, like actually a list of people, so like person. I'm very old. I have 15 years old. Person. I think it's 24. Person. Okay, so we have a list of people. Okay, now think about this list. Okay, let me. So suppose that the state of your contract is this list. So suppose that you want to access the third slot of this list. What happens on Ethereum is that this list, it's not saved on the contract as it is. What happens is you have to serialize this list, and this serialization needs to be done by the contract. So the people that implement the contract, it needs to come up with a serialization scheme, okay, to take this list and store it in the global memory. So for example, that person can come up with the following scheme. A person will be like, because the state of the network is just, the global state is a map of word to word, okay? So the person that implements the contract, it has to come up with a scheme of representing this inside this. So for example, you can say that a string will be a single number, and then you can only have like up to 32 characters, I believe. And if you want more, perhaps you can make a string use many characters. So like you reserve 3 words for the string, or perhaps like you can come up with a scheme that a person is stored in a single word. So like you have like half of those bits used for the name and 1 bit used for the age. And then you can like have that the index 0 is the person 0 and the index 1 is the person 1. But again, if you want to use more space, you can reserve many index for a single person. So like the point is, the people that implements the contract needs to come up with a way to convert to bits, okay, to convert it to words. That's what happens when you program on Ethereum. And the problem is that when you want to read this, you also need to do the reverse. So you need to take those binaries and revert back to a string and to the age and something else that you have in this structure. And so every time you call a contract, you need to deserialize from this buffer, from this memory, into the actual structure. And then when you want to save, you want to serialize again. First, that takes a lot of computation. And second, that's not very efficient in memory. So on Kindelia, instead of doing all those computations every single transaction, so like if you think about this, if like 8% of the gas like if 8% of the gas of a transaction is just serializing and deserializing from here, and that's actually kind of what happens because this is the most expensive operation on Ethereum, and then you also need to add computation on top of that to reconstruct the actual structure. So if that happens, then you can make a blockchain faster, 5 times faster, even without changing the model of computation, by just not needing to serialize and deserialize every time. And that's what happened on the old Kindelia. So the idea of the old Kindelia was, instead of having those operations, what happens is the memory, this memory, like this local memory here, that's erased when the contract returns, we don't erase it. So we keep it. We keep it for the next block. So like we keep the memory for the next block. So
In the
we
blockchain.
just inside the blockchain. So when you run this, the leftover memory will not be erased. So when you call the contract again, you can still have access to the memory of the last time this contract was called. And what is this memory in the case of Ethereum? It's just numbers. What's this memory in the case of Kindelia? It's interaction net nodes. So for example, this on Kindelia would be represented as constructor, something like this. Cons person Victor 15 cons, and like this structure, if you have this in memory and you just keep this in memory, this is saved, this is persisted, okay, through all calls of the contract, okay? This will never be erased unless you want to erase it explicitly. So this is good because you don't need to take this and convert to something else every time. It's always there in memory, okay? And so and to do that, what we do is we take the memory, okay, the memory of the contract, and we keep it, and and the problem of doing just that, like suppose that you just keep the memory, okay? So now we have an update. This becomes a 2 in another block. But this block now is rewritten, okay? So there is a block reorg. So we are back to this block, okay? Why this happens? This can happen because someone else has mined another block in the same hive. Don't know how to say this word. So someone else mined another block in the same ID, okay? And the block has a higher proof of work than this one. So this will never happen. This is like a fake history, and we'll go to another block in the same number. But when this happens, if we have just a buffer in memory in the node that's running in the computer of everyone, if it's just a buffer, we have rewritten that buffer. So we don't know what was the old state. So we need to save the state of all the buffers. But like if the memory like has a gigabyte of state, okay, the global state is a gigabyte. But now we need a copy of this gigabyte for the block 1 and the block 2 and the block 3 and the block 4 to allow us to go back. Okay, so now we need like 7 gigabytes to keep all those old states. So that's not viable. So the idea is that instead of keeping the whole state, we keep just the diff of the states. So for example, if from here to here, we change just this number, this block will reference to this old block with this specific change. So that was the block hierarchy, like buffer thing that we had before. Okay. I like this a lot, actually. I think this is a better way to do things, but these had problems in the old kindelia because you code construct things that leaked memory, and all contracts share the same memory. And when that happens, big trouble, because we don't account for that, and someone can flood the memory and spend the memory, and then we'll never know. But that only happens because of this garbage collection problem of the HVM. So the thing is, on this new version that uses interaction combinators, there is no garbage problem at all. No garbage problem. So in theory, we could use that. Okay. Why I'm not using that? I don't know. Actually, I don't know. I think I'm just being like overly cautious to not implement anything fancy. So instead, I just have like a global tree as the memory, and the contract just updates this tree. So I don't keep like all those nodes in memory. It's like I'll not say it's simpler, but it's less fancy, okay? And since it's less fancy, it has less chance that, like, less chance will screw up the code, okay? So in short, like the main reason I'm not using this anymore is like to protect us from like messing up with the code. Perhaps I'm a little bit traumatized because like people usually tend to mess up things. So I just want to keep things as simple and as brain dead as possible. So there is a small chance that we mess up. But if you guys think you can do it that way, the amount of code will actually not be much bigger and it will be more efficient. So I'm open to doing things this way, okay? But like to keep things more safe and like and to be more cautious, I wanted to just have a tree as the state and not have this like block hierarchy scheme, okay?
Okay. How a question. I think I also I think that it's better if we like quickly ship the kindelia as simple as possible. And that feeds my next questions with which is how open to change like how would it be possible for us to re-implement this, like changing from a from the tree to this reversible heap thingy? Would it be possible for us to change later, or like once we deploy the net, it's we can change it up?
Yeah, to be honest, I think this is a decision that you need to do right now because it influences even the language that will be used, like the way that contracts will be done. Because like if we want to have like a tree as the contract, when you are a contract developer and you want to update the state, you need to change this tree and return like what changed. So implement the contract this way. If you want to do this, it's actually much simpler to implement the contract. You just have like you can implement the state of your contract as any lambda encoding or like any interaction net, and you don't need to do anything. You just like leave the memory as it is, and you are able to access the same memory again in the same block. So we have some notion of persistence that's different. But the problem is that changes how we implement contracts. So it's not something that we can change later because again, that's like the contracts needs to be done in a way that's specific to each one of those designs. So it's not something that can be changed.
I see. Is there any other
Oh.
blockchain that uses this design?
Not that I'm aware of, but I have not been following the blockchain area for a few years already, so I don't know.
And you say the state should be a tree. Would the contract then update the state by basically declaring transactions on that state so that it could also be undone?
So what happens is each contract has access to when you call a contract, what happens is the contract is like a function that receives some arguments And you can think about a lambda function, okay, that receives some arguments and can do something with that arguments and return the new state, okay? So these arguments is something that we send to the contract that includes the global blockchain state, which includes like everyone's balances, and it includes like everyone's balance, the global blockchain state, like this the block number, time, I don't know, not time, like some other metadata. I don't know. I'm probably forgetting, but like some other metadata. So the contract has access to all this data inside this lazy structure here, okay? And it returns a new state. And the thing is, you need to think about the global blockchain state as a tree, okay? So let me do it like this, like it's important to understand that this is a little bit different from Ethereum, because on Ethereum, like the state that a contract has access is a map from word to word. So like let me draw let me like Ethereum contract state. On Ethereum, the local state of a contract is a map of word to word. On Kindelia, it is a tree. And what's a tree? It's this type. Okay, that's all. So instead of having access to this type, we have access to this type. And then I perhaps need to elaborate on why this specific data type is a more general way to implement states. But before I do that, let me talk about the global state of the network. So the global state of the Kindelia network, you can think of it as a tree. So there is the root of the tree. This is the root of the tree. And from here, everything else is underneath it. So we have like this is the root. Is the root. This is the balances tree. And again, I'm just like being arbitrary here. It could be some organized in another way. I'm doing in this way just for example. And this is the root of the, okay, this is the global root. This is the root of the balances. And this is the root of the contract states, okay? And now to access someone's balance, you need to traverse a path that's equal to its address. So like if its address is 101, you'll go through this path. 101. And inside here, we'll have, let me gain more space. And inside here, you have the balance of the user that's also organized as a tree. So if the balance is 4, it's 0, 0, 1 in binary. So like something like this. And then the tree ends. So let me draw some leaf nodes. Okay. So suppose that an address uses 3 bits, okay, 3-bit address. And suppose that the balance uses 3 bits. And again, I'm using just 1 bit to, okay, I'm using 1 bit to define if you are on the states map or the balance map. So this is a simplification, okay? So under this simplification, there are 4 parts on this tree. The first part is the root. The second part is the, like, is this a states or balance tree? The second part is the address of the user. And the third part is the balance. Okay, I forgot to type here. Balance. Okay. So the thing is, by walking through this single same data type, we have access to all the data of the blockchain. Okay, all the data of the blockchain is encoded in this big tree. But keep in mind that the local state of the contract, let me make it here. I should have done it actually. So the local state of the same contract, suppose that the local state is this address. So here is the address, okay? And then we have the local state. And suppose that for the local state, the contract can have a tree of like 32 depth, okay? So like it's a tree here that can have up to 32 bits, to 32 depth, and the contract has complete access. So the contract can use whatever scheme he wants to organize this tree. We don't care, it's up to him. It can like be a map of like 10 bits addresses to 10 bits balance. It can be a map of like 8 bits locations to 8 bits items if it's some kind of game. We don't care, okay? We give the contract access to the same structure here. So this is the address and this is the state. So when the contract is called, so again, the contract is like this lambda, not lambda because it's an interaction net, but you can think of it as a lambda. So the contract is like this function that receives an argument, and that argument includes the root of the whole blockchain. So by inspecting this argument, the contract can access any data in the network, including his own state. So how can a contract access his own state? It must go down to the states tree, and then it must go down in its own address. Okay, so like he probably receive its own address here too. So he can access its own state. And now he's here, okay? And now he can do whatever he wants with here. And when the contract returns, it will return the new state. And that new state will replace this thing here in the global state tree. And it's also important to understand that contracts can access directly the state of any other contract. How? We just like go, like we start from the root, you go to the state, and you go to the state of another contract. You can do that, okay? So because the contract has access to the state to the global state root of the whole blockchain, okay? So he can access any data on the blockchain, the balance of someone, the state of some contract, okay? And by the way, since I'm talking about this now, under this design, and by the way, guys, just to be clear, this is my design. You can change it, okay? If you think something here is not good, you have the freedom to discuss with us, and this can be changed. But again, under this specific design, the way that contracts talk to each other is not through call. Okay, that's also something that changed because it was very complex to implement on the old kindelia, and it's also a source of complexity on Ethereum. And we want to make the node as simple as possible. Okay, even if it makes contracts a little bit harder. And why we want that? Because it's easy to change contracts in the future. We can make libraries. We can make communication libraries. But changing the node, the protocol, is much harder, okay? So we can cover up complexities in making contracts with great libraries, with great language. But you can't change the protocol. So if the protocol has something that's complex, it's there forever. And the way that contracts talk to each other on Ethereum is using call. And if you go ahead and look like Ethereum opcodes, you actually see that there are like 3-4 different calls. Okay, there is call code. I think that's actually to access the codes of a call. But there is call, there is delegate call, there is static call, and there is another call to create contracts, and there is another create. So look at this mess. Like it's very messy. And the revert itself, because like it's complex and it's very easy to get it wrong. And they got it wrong. So that's why like they have so many versions of calls. So we want to avoid that. So the way that we do communications for us contracts on this specific implementation of kindelia is by reading the memory of another contract. So for example, you have an exchange, okay? You implement an exchange. And then there is a game, the cat game. It's a very Fibonacci. Is that how? So there is an exchange to exchange tokens, and there is the Fibonacci game. So the exchange wants to allow people to exchange tokens on the Fibonacci contract. So how this works? The way this works is, in order for the exchange to send a message to the Fibonacci contract, what it does is it changes its own memory in some kind of like something like this. Like the exchange will do this, okay? Self.memory dot outbox. So like an outwards mailbox dot Fibonacci. So it changes its own memory in the outbox slot, in the Fibonacci slot, in the message record, and then it writes some memory here. And how the Fibonacci contract gets this message? It needs to explicitly access global root dot states dot the exchange address dot memory dot out mailbox on address message. So like the exchange saves memory to its own memory, and then the Fibonacci contract needs to read memory from the exchange. And of course, for this to happen, they need to understand that each other exists. How can they do that if they are deployed after? Like it's a Turing complete language that you have. So like you can come up with a communication scheme that allows people to do that. But again, this is something that the users need to come up with, okay? This is not done by the protocol. So of course, like we probably come up with our own standard of how contracts do communication, but it's not part of the protocol. It's a standard that's outside the protocol, like in the same way that like, for example, Ethereum has tokens and it's not part of the protocol. It's a standard that someone has made, okay? So in the case of kindelia, communication will be a standard. So we have like probably something like KRC70. That's the communication protocol that the users invented for kindelia. Okay, so because communication will not be handled by the protocol, it will be handled by the contracts themselves. Okay, and they need to use this like global memory reading schemes to implement communication protocols on top of the network. Okay, does that make sense? And again, if you think this is too complex, like change it. Like, but again, you need to measure the complexity of having this in the protocol if it's worth. Okay, because what I'm doing here is basically I don't want to deal with this in the protocol. I want the protocol to be simple, and I want to move this complexity to the library level. Okay, to the language. And I think that's the right direction because we have a functional language, and like functional languages are great at modularization. So we can have like a very good communication protocol in the kinds language. Okay, but if you think that's not a great idea, again, you are free to change it. Okay, does that make sense?
Yeah.
Yep.
I'm just
Like-
wondering.
Yeah.
Let's say there's some kind of exchange or something, like Uniswap or any other exchange, and then it doesn't, like the authors of that exchange don't want to have to know about all the potential clients that call it. Like with the public API, for example, if you have a public API, anyone can call it, do something, do some requests on it, and it replies to whoever called, but it doesn't need to know in advance which IP address client would have that would call it, especially not before it's being deployed. So wondering how it would work here. Allow calls from anyone.
There is no calls. You can only change your own memory.
But I mean, on a semantic level, like on a higher level, if you think about it in terms of message passing or calls.
Yes, you can even like just have a contract that's the communications contract that registers everyone and does this dispatching. Like you can do anything. It's Turing complete. Anything that you can do in the protocol, you can do with a contract. So
Yeah, but
Of
wouldn't
course,
that
like-
contract be the bottleneck for smart contracts that need to communicate?
perhaps, but then we can optimize this contract with like explicit code in the node. So we can leave this this. Do you see what I mean? Like we can leave this as an optimal optimization that in the end will be like the same thing because it will be implemented in the node, but you don't need to implement it in the node to be able to, for example, read the state of the blockchain offline. If you just want to make some kind of offline script to read the state of the network. So that's better, you know what I mean?
Another idea could also be in terms of message passing that instead of just having contract states and balance, we could also have like a box of messages. Then they
Yeah.
also get that as another input argument. That would also be a possibility.
Yes. Again, that's the simplest thing that we could do, other than what I'm doing. Like that's way simpler than actually calling the codes of the contract and delegating calls and async and all those things. So yes, having a mailbox is simpler, way simpler than what Ethereum does and what Kindelia done in the first version. But it's a little bit more complex than just having this, because this you don't need to do anything. Like you just allow contracts to read memory from each other and then they can communicate. So, and again, it's a very small code to add an inbox, like you said. So perhaps it's worth, perhaps it's not. It's up to you, okay? But it's more code, okay? It's some complex. So you need to think, even if it's a little complexity, if you want to have that complexity.
Yeah.
Because again, right now, like the design is pretty much based on the philosophy of make things as simple as possible, ask questions later. So that's like what I'm trying kind of to do here. And of course, like that's perhaps too extreme, but that's the way I'm doing right now.
And we will also we will have a test net, and then we will get experience, and we'll already notice what makes sense and stuff. But
yeah,
I think it's definitely message passing is definitely simpler than calling and then waiting for the response. And you could even have like just like in Rust where you have async, you can implement that over Rust channels in theory if you wanted, or like over any transport mechanism. So similarly, if we had message passing, even if that message passing would be implemented in terms of this output state, then people can chain so-called calls in an async way in their contracts, even if they're not actually calls. It's just layers of abstraction.
yes, exactly.
And would this tree be a Merkle tree?
No. So the idea is that we don't want to use Merkle trees. That's what I defend. But if you really want to, you can go ahead and do it. But that's also worth mentioning. So yes, I forgot to talk about this. So on Ethereum, this operation, it needs to change a global Merkle tree, and that's very expensive because a Merkle tree is pretty much like a big tree, okay, like any other, but like with like a lot of depth on it. And the problem with a Merkle tree is that every single pointer, instead of being like just a normal pointer, like a 64-bit pointer to the address, which is like normal, it's like how trees work in every computer ever. What a Merkle tree does is that they replace the pointers by a hash pointer. So now the pointer is the kechak, is the hash of the structure. So first, these use 4 times more bits, which is already much bigger, but that's not the problem. The problem is that hashing is way more expensive than just saving an index. So when you need to hash 32 times, every time you want to store a single bit of data. So like you just want to change the HP of someone. Like you want to update someone's HP from 5 to 4. It's a single bit that needs to change. But on Ethereum, to do that, you need to like take 1 hash, 2 hash, 3 hash, a lot of hashes. So the store operation is very expensive on Ethereum, not just because it uses global persistent data, but also because it's computationally expensive. So While I like in the reversive happy scheme that we had on the first kindelia, we did not need to do that because did not need to do anything. The memory is just there. We just leave it there. There is no hashing. There is not even saving. There is nothing. It's very like the reversible happy is like the less expensive you can have for the store operation. In this new model, that I'm kind of not sure if you should do it that way, but the state is just a tree. And when you want to save something, sure, we need to do this and this and this and this, but we don't have a Merkle tree. We have a normal tree. So it's just a normal tree writing operation, which is like hundreds of times less expensive than the Merkle tree. So the idea that we have is like less like cheap than the reversible heap thing, but it's not as bad as having a Merkle tree because we just want to have a normal tree. So like it's pretty much an innovation that's just not doing something. So it's not really an innovation. Like it's just let's not do something complex that does not really need to be done. And then you might question, but does it really not need to be done? Like it's not that there are good reason to have miracle trees, and yes, there is. There is the way to have light clients, but that's kind of half a lie because we have this for years on Ethereum and we still don't have light clients. It's very complex to have light clients, and by the time the technology is there to have light clients using Merkle trees, it will probably be there to have light clients using ZK snarks. And with ZK snarks, we can have light clients without Merkle trees. So in my opinion, Merkle trees are pretty much like a complication that don't contribute to anything. So let's not have it. Okay, so the two options that we have is we store states as trees, or like we store states as reversible heaps. Okay, and again, I'm still tending towards having trees because it's just much simpler to explain and implement and things like that. It's a little bit less performance than reversible heaps, but it's still way more performance than the Merkle trees that Ethereum had. Okay.
Mm. And by the way, when Googling reversible heap, the first search result is in the kindelia subreddit. I'm wondering, is it how you describe that the old, so you would send a diff of the state as part of the contract.
You need to ask Kelvin. This is not a new thing that we invented. This is used, for example, by Linux, the kernel of Linux, to deal with file buffers. So it's a very old technology, actually. We just have like all those buffers that refer to each other in a layering fashion. So for example, if you have this buffer on the block 0, and on the block 1, you have this buffer. And on the block 2, we have this buffer. So what you need to do is you don't need to save all those numbers. You just save those first numbers. So those here, and then you save the ones that change. So this block only saves this number and this number. And this block only saves like, yeah.
So it's like kind of like software transactional memory, or just transactions basically on state. Those transactions can be integrated over the series of like increasing indices.
Yes, yeah. So,
final
and
state.
what we did also is that instead of saving all the blocks, like all the diffs, we actually only saved diffs of blocks that, with like the older the block is, the more likely it is for us to not save it. So for example, if you are on the block on 1,000, we save it 1,000, and this one, and this one, and like 4 minus that, and then 8 minus that, so 5, and then 16 minus that, so like this, and then So like the older the block is, so like we just like save, you see like like you don't save, like we save like the more recent blocks more concentrated, but like older blocks less concentrated. So in the end, we only need to save like a few blocks. And Hank, no, I don't think that's the case. Um, no, that's not right. Like the reason, um, intensive to check if the state changed. Um, like no, okay. The reason Merkle trees are implemented that way is to for us to be able to make Merkle proofs. So what's a Merkle proof? You want to prove that, um, for example, if you have this tree, let me draw it. Suppose that this is a big tree, okay? I'll not draw all the branches, but like suppose this is like a big tree. So you have many numbers here. So like 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose that this is the state of a contract. And suppose that this, like each number is the balance of some user. So this is the balance of an user, this is the balance of another user. And
Hello? Hello? Hello?
Hello.
Rip. Just, just a heads up, in about like 20 minutes, I'm gonna have to take another call, but I'll ask Taylin later to send me the video for any missing parts. Hello? Hello? Hello?
He's probably still talking on his house.
But I mean, I guess we have 90% of our doubt censored at least, right? Um, where should we begin? Should we like
There was
draw?
one question that
Sorry?
I still had before he disappeared.
Yeah.
Well, because like with proof of stake, there's the question of the initial token distribution needs to be solved or addressed, and also proof of work is much simpler to implement than proof of stake.
Mm-hmm.
And one of the ways that the initial token distribution can be done is by first having proof of work and then transitioning to proof of stake later. How Ethereum did it. And could also make sense for us because if we want the first version to be as simple as possible, and yeah, proof of work is much simpler.
Oi, oi, oi. Hello, hello.
Hello?
Mas você quer em 5 minutos, viu? 6
Ok.
agora.
Internet não, eu tô aqui desesperado tentando conectar. Aí eu consegui, eu conectei do celular. Tô no 3G
Eu
agora.
pensei que você estava falando sozinho.
Ah, eu devo ter falado sozinho por um tempo. Não sei quanto. Vocês pararam onde?
Eu tava respondendo minha pergunta ali da Merkle Tree. Merkle Proof, você tava falando.
Sim, eu sei, mas onde que eu parei nessa parte, dessa Merkle Tree?
Tava explicando o Merkle Proof.
Tá. Ah, eu cheguei a começar a desenhar essa árvore?
Sim, sim,
Entenderei?
sim.
Ah, então foi. Então
Ela
tudo
chegou
bem,
até aí.
lógica. Tá, então foi exatamente o que eu parei. Então, tipo, tem essas, tipo, tem uma. There is a Merkle tree, ok? This is from the cat coins contract, okay? When contract of this application opens his application on the phone or something like that, the client, the software, needs to know how many cat coins Alice has to show her, okay? So like the software needs to know how many cat coins she has, so it's able to show her balance. So you have 4 cat coins. So how can the client, the front end, know that information? So normally, it's a decentralized network. So in order to do this correctly, the front end, the application that Alice is using on her cell phone, smartphone, needs to download the entire blockchain and run all the contracts and do all the computations so that it can like create the database, the state for the cat coins contract, generate the balance of everyone, and then the client will know that Alice has 4 cat coins. That's a lot of work. That's very expensive. So the other option is just ask someone, like just go to otherscan.com and ask someone that has a full node how many cat coin Alice has. But the problem of that is that requires trust. And by the definition of the decentralization of a blockchain, if everyone does that, it becomes a centralized network. So you lost like the whole point of the thing. So we need to have a way for you to know your balance without needing to download the whole blockchain. So that idea is the idea of a light client. So what light client is something that downloads a small percentage of the blockchain and can tell your balance. Okay, so you don't download the whole blockchain. You download just a part of the blockchain, and you can still tell your balance without needing to trust anyone. Okay, so that's a light client. Okay, and it's not necessarily a balance. It could be like the items that you have. It could be the state of some game. It could be the balance of someone else that you want to check. The point is, you can consult something about the blockchain without download everything. So how it works on the Merkle tree, on the Merkle tree scheme, the idea is you ask someone that has a full node, what's your balance? But instead of the person just sending you, hey, your balance is 4. Like you have 4 cat coins like this, and you just trust the nodes that this information is correct, like just send a single number. Instead, the node will send you have 4 cats. The proof is. So it will send a proof that you have 4 cat. And what's that proof? That proof is the root of the blockchain state. So the hash of the whole blockchain state plus a proof that this hash is the right hash of this block number. Okay. And then that person will send a proof that inside this contract, this number is 4. Okay. And to do this, you need a Merkle tree. Okay. So the reason that Merkle trees exist is for you to be able to create a light client. So it's not that very important. It's not that something that you want to have. What I can tell you is that while Ethereum has this feature since the beginning, it never had a light client. So Ethereum survived like almost 10 years, and nobody ever used light clients up to this date because there is no light client implemented. Why? Because it's actually very complex for many other reasons. So again, Ethereum survived for almost 10 years without a light client. So I think that kind of shows us that you don't need a light client, okay? Because usually, like people think that there are three kinds of users, like hardcore users, so on Ethereum, the Ethereum network is designed for this, and semi-hardcore. So Ethereum is designed for this world. So there is the hardcore users that download the whole blockchain and know everything and have all the proofs. There is the casual users that don't care about proofs and that can't exist. So Ethereum thinks that this does not exist. And then there's the same hardcore users that want light proofs for the thing. So they don't want to download the whole client, but they want the proof that everything that they're seeing is correct. They want absolute proof. That's not the real world. In the real world, this does not exist. And you have hardcore users that want full proof, and that's important because those are companies, governments, like billionaires, like something like that. Like it could be also full node altruistic operators. Because we need those people to keep the structure of the blockchain. But everyone else, they don't want a proof that their balance is 4 cats. What they do is they know some hardcore user that they trust. So, for example, myself, I probably know someone that has a full node, and I ask that person what's my balance, and that person will tell me. So the light client, like nobody, there is not much use for a light client. So I and I don't think that sacrificing so much of the performance of the blockchain for something that no one uses is not a good idea. So Kindelia will not support light clients. And even if that's the case, we can still have light clients based on ZK snarks if you manage to compile interaction combinators to ZK snarks. So even if you really want to have light clients, there is a better way to do light clients than Merkle trees. So like there is no reason to have Merkle trees. Okay, that's my opinion. Okay.
Yeah.
Yeah.
And even until we have ZK snarks, we can also implement like a balance check by just asking a bunch of random full nodes in the network and then checking if they all say the same balance, if they
Yes,
differ. So you don't have to trust a single one.
exactly. Like it's like like sometimes like the blockchain developers, I think that I don't know, like it's a little bit of out of touch with how things are actually used. Because like there are people, because the problem is some people are like, we need decentralization, and then they want to decentralize everything. And things that do not make sense to be decentralized. And then they get up with a product that has no UX and no usability. And then there are the people that don't understand decentralization, but they are in the hype of blockchain, and they end up making things like centralized blockchains that are like an Node.js server because they don't understand the reason that things are decentralized. And this destroys the meaning of decentralization because now someone can change the database. So you can't trust that you have those amounts of coins forever. So that's two streams that are both wrong. What we want is we want a guarantee that no one can hack my account, but it's fine. I can't trust someone else when I consult my balance on the front-end application. There is no hacker from FBI hacking my front-end application to tell me I have 3 cat coins instead of 4. No, that's not the problem that Bitcoin solves. The problem that Bitcoin solves is that the government can mismanage like the currency and we don't trust it. And like when you have some assets in a game, I don't trust that the company will not shut down the game and then I'll be out of job. So those are things that blockchain solve. They remove the trust in companies, the trust in governments. But it's not about making like the front end application of every single user um, protected against any kinds of hacking. That's not the point. That's not the point. People don't get it. It's like the decentralization of a blockchain is to solve major like big scale issues with like currencies, with applications, with things that on the long term can go wrong, like with the with the balance of a coin circulation in that circle. I don't know how to say that in English, and things like that. But you don't need to have like that level of protection in the end user, and that does not make any sense. And like both ways are very extreme, and we need to understand the balance of what makes sense and what do not. Okay.
Yeah. And by the way, do you have you looked at this paper about compiling interaction nets to arithmetic circuits for these ZK snarks or zero knowledge proofs? Do you think it's a possible or feasible thing that we can have in the future?
Yes, I have read it. We know that HackerDoc also has read it. I think it's a brilliant paper. It uses traces. It seems like a very good approach. I have no idea how it works. I have no idea if it works. I did not have enough time to explore it. But once we have more budget, we for sure want to hire people to work on that. But like since this is an optimization, and since the budget that we have right now is not infinite, I don't know how to say that. We don't want to spend a lot of money in things that are optimizations, as good as they are. So right now, like let's focus on doing the blockchain, and in the future we can have like CK snarks.
Yeah, sounds good. And there's another question that came up is because with proof of stake, there's this question about how to solve the initial token distribution. And also proof of stake is conceptually more complex than proof of work. And like, for example, one solution could be to start with proof of work and then have like the initial test net already with that, and then transition later to proof of stake. That also solves the initial token distribution. Otherwise, we would have to find a different solution for that. What do you think?
Yes, I think that's fine. Like again, I don't have strong opinions about how the consensus algorithm will work. I just want something that works. Um, So yeah, like we can like start with proof of work and then migrate to proof of stake. We can start with proof of stake if that's even possible. We can go proof of work forever if people agree. Like I'd rather just not because like I know I'm the minority. My vote is to like just have proof of work forever. But if that will make people not come because people just want proof of stake, like they are wrong, but like they want it, so what can I do about it? So like let's just use whatever is most popular and people want as long as it's safe.
There's also, for example, proof of activity, which is a combination of proof of work and proof of stake. And the proof of work is used for preventing double spending, and proof of stake is used for preventing centralization. It's also, like in terms of energy efficiency, like if that's the main argument why people want proof of stake, it could also make sense to have kind of this hybrid model. Yeah, I
I
think
really like
for the
hybrid
initial.
models. Go ahead, sorry.
Sorry, what did you say?
No, I just said that I really like hybrid models.
Yeah. There's definitely nowadays there are like so many different consensus algorithms. They all upon the earlier ones, like delegated proof of stake and all this. But yeah, proof of work seems to be the easiest for getting something working as soon as possible, like a minimum viable product, so to speak.
Yes. And again, I think that's the most important thing about the consensus algorithm is that it's not going to make your code how do we say embananado in English, guys? I don't know.
Messi.
But
Say
that's not just justice.
embananed.
Embananed.
He's
So
going to understand it.
let's not make the code Gambiara. Let's make the code like that because like the networking is where like things can go wrong and like it's the most complex thing to do, but it's also the most avoidable thing to do because again, we want to use things that are working and tested and like used by other networks, so libraries. So as long as we find the right libraries to use, I don't think that we should like if you find a great library that use proof of stake and just works and we can just install with with Cargo and it just works. Like it's I would rather use proof of stake just because this library exists,
I
like
think it's messy, Victor.
Mass does not do justice to the
Yeah, it's like
environment.
fuzzy.
Embananado.
Fuzzy,
No,
maybe, perhaps.
Like kind of
no.
messy.
I don't think there's an equivalent word
Guys, I
for
get it. Okay.
empanada.
So, okay, does that make sense?
Yes.
Everyone is on the same page. Where is Henky?
I think I had to leave him because he has a call is scheduled for
Okay.
4 p.m.
So you want to continue another day? Is there any question that you want to ask me?
So for the initial interaction combinator VM, should we use the current interaction calculus repository and then make it parallel, or what should we start with in terms of that?
I will just copy and paste the init.rs file from the interaction combinators calculus repository, and then perhaps take some things from it, like perhaps serialization, things like that, and then just adjust to the way that kindelia works, because like the reduction function, we don't want the one that's on the interaction calculus repo. We want the one that just has all the redexes in a buffer and does it in parallel. And we need to add some locks, so probably want to replace the memory from U32 ints to atomic ints. Like we just want to do those adjustments and keep it as simple as possible. I think that Deranash has done some of that work. I don't know. But yes.
I haven't changed the interact combinators. I just copy pasted it into the repository and used it the 150 line one.
Yeah, so it's exactly what I said. So probably just need some adjustments for the parallelism, and that's pretty much it. Like, let's not overcomplicate. Some things will be very simple because the protocol is very simple. That's good. That's not bad. So like, again, and I don't like if everything goes in the best possible scenario is that this project will be very easy. So like it will be overkill to have all you working on it, because if all goes well, it should be like 1,000 lines of code and it's running and it's working, and it's fine. That's what you want, because like if it's released in 1 week, and that's possible, like it's possible that in the next week you have a working version with synchronization and all those things. Because again, the main work is like doing like the contract integration, the state, the serialization, saving, and then doing the networking. But like it's all like it's not a lot of things to do. And like if in the next week we have a working version that's almost close to the final version, great. Let's focus on doing like the blockchain explorer. Let's focus on doing applications. Let's focus on doing a lot of libraries. Like I said, if the protocol itself is very simple, we need to write a communication standard. We need to write a token standard. So like most of the time, we want to be spending after the initial client is done. And that's great. That's what we want. So let's keep the client simple. Let's release it. And when the initial client is done, and of course, like it will be impossible to use it because like it's very low level. Like it's interaction combinators that we need to write by hand, and there is no like libraries, there is no numbers, there is nothing like, and even communication needs us to do a lot of effort in the contracts itself. So it not be very usable, but it will work and it will be stable. So that's what you want. And then we can focus our time in like taking this small thing that is hard to use but stable, and adding all the libraries on top of it, the ecosystem, the standards, to make it usable. Okay, so first we make it stable and simple, and then outside of the protocol, we make all the infrastructure to make it usable. And most of the time of the team will probably be spent after the client is working and stable. Like I think, like again, writing the blockchain explorer, writing the specifications, writing the standards, writing the wallets, doing all those
documentation.
things will take a lot of time. Documentation also, of course, like most of the time, I want you to be spending on that. So let's make the client happen as fast as possible because the real work starts after the client is working. That's what I want to say.
I think we also need to implement the virtual node on the interactive combinators.
Yes.
So you can access the state of the contracts without having to copy the whole network into InteractNet.
So I'll talk about this a little bit here because I believe Oliver will be able to understand and help you with this implementation. So are you listening, Oliver?
Yes, yes.
So do you remember this current proposal of how the contract accesses the state? Like it receives the root of the tree of the entire blockchain state, and like it can navigate through this tree to access anything that's on the blockchain. Does that make sense for you?
Yes.
But the problem with that is that if this state is stored on the blockchain as like, suppose that's a Rust structure, like tree, like it is a Rust structure, okay? So tree, it can be a node, box tree. Suppose that the state is actually saved as this, like as a Rust tree. So like we take this, we make the like turn this whole thing into this Rust structure and we save it. Do you agree with me that first, this will take way more bits than necessary? This will be like huge. That's not very efficient. But the problem is not that. The problem is when the contract receives like where is the contract? It's not here. But I'll write here. So like when the contract receives this argument, we need to convert this to an interaction combinator. So pretty much we need to like, what you probably want to do is we want to convert this tree into a lambda encoding. So like something like that. So a very, very big thing. So like this whole big tree is converted to a very big lambda encoding. And then we convert this lambda encoding to interaction net. So like those triangles. And then like we send those triangles to the contract. But like if you do that, every time a contract is called, we'll need to convert the whole state every time the contract is called. So that's totally stupid. So the idea is, first, we want to save this in a more efficient format, like some kind of buffer. And second, we want in the interaction net a new node type that is a lazy reader. Let me call it a lazy state reader. That's just a node that when it's just a single node, but when we interact with it with something else, it will split itself as if it were a lambda encoding, like in the same way that a lambda encoding would, but like it would become like lazy state reader 0 and lazy state reader 1, okay, split into different nodes that now are focusing on a different part of the tree. And then you can like keep interaction with it, and you are not like allocating this whole big interaction net with thousands of triangles. We just have a virtual node that interacts as if it was this big tree, but it's not because it's reading from the buffer. Does that make sense?
Yeah. And would we have the same like, output also?
Yes,
Or
like
is
it
the output
behaves
just
exactly
deserialized?
like it. Oh, sorry. Oh, no. So the output, you mean the new state, right?
Yeah.
So the new state of the contract, the way I think this will work is that it will return a diff tree. So because for example, suppose that the contract is a coin and it has a map of balances and it has 1,000 users. So like there is 1,000 entries here, like 1,000 balances on these like contract states. So if the contract needs to return the whole tree every time, like you need to convert this tree to the buffer, and that's very expensive. Like every time the contract needs to encode its whole state and whole again, so the idea is that the contract will just return a diff tree. So like just the paths that need to be changed, and then we'll traverse through this tree and change the bits in the compact buffer. Okay?
Yeah.
Does that make sense?
Yes.
Okay. So that's the idea that I had. And again, my design has a big problem that I completely forgot that contracts need to send balance to other, because since we have a native coin, the coin system is different from the state. Like the state is already enough to make hold on. The state is already enough to make tokens from the user. So tokens that the users can deploy and send tokens to each other. But the native token is different from this system. So there is no way for a contract to send native kindelia tokens to another one, since it is only returning the new state. Okay? So while contracts can talk to each other, they can't talk to the coin of the protocol itself. So we actually want perhaps to return a tuple of the balance, the new balance diff, and perhaps some kind of information that allows the contract to send money to some other contract when it returns. Okay?
Okay.
So that's a small update that you probably want to make, that I overseen in my initial specification that I sent to the Renash.
Yeah. By the way, do you have a link to that specification? Is it a GIST or
Yeah, the
GIST?
Renash has it.
I sent it here, but it's in Portuguese.
Ah,
Oh, GPT-4.
I can translate it.
It's
Okay.
So many things. But guys, honestly, I'm very optimistic. Like I'm honestly never have been so optimistic as I am right now that the network will happen and Kindelia will work and everyone will be happy and everything will be great. Because we had the experience of implementing Kindelia before and we know what the mistakes were. And the new design solves all those mistakes. It's much simpler and it's very easy to like we have a team that has people that I have seen that are capable of doing what needs to be done. And I actually think that you are way like more capable than what would be necessary. Like I think Oliver alone would be able to do it. I think Nash alone would be able to do everything that needs to be done. So like you all together, I think it would be a piece of okay. I think it would be like very simple to ship this initial version. I think the version will work great because it solves the all the problems that the other one had. Even problems like the checksum problem were problems that happened because of the way that we did the HVM. So like all the problems that we identified are solved. It's much simpler. So I don't see anything that could like go very wrong. I mean, the only thing that perhaps could go wrong is only a matter of us finding something that can be used. So like I'm very optimistic, guys. Like I'm very optimistic. I think that this team is in a very good shape to make this like and I think and I like and of course like I would be more worried about like I'm more worried about people not using it than we're not being able to ship it. Okay, that I think should be the main concern. But again, it will not be your fault. Like but even in that consideration, I actually think that it will be something that people will use because it will be a very simple blockchain, and that bit itself is very attractive. And the whole parallelism and the performance, and if you manage to have great benchmarks, so like, and again, it's late. The problem is that it's late to have some like new layer one blockchain like that. So because of just that, perhaps like there will not be a lot of attention, but yeah, it's never too late to great products, and it is something that's like that does not exist in the world today. Another day, I have read a comment on Reddit that someone just said, "Hey, all the new blockchains that have smart contracts, they have like these whole complex things that VCs put on them, and there's a lot of complexity. And you don't have a blockchain that's as simple as Bitcoin that has smart contracts." Place. Okay, so and again, even if like no one uses it, like we have done our job So in the very last, I think that we at least will be completing our mission. But I even think that it will be something that people will want to use. So I'm optimistic in all fronts, like in the capacity of the team to deliver, in the design of the blockchain to work and to be stable and to be fast. And I even think that people will be using it once we start doing things on top of it. So I'm very optimistic. I never have been so optimistic about Kindelia like I am right now. And I really think that you'll be doing a great job. And like, especially now that like Oliver will be taking the leadership, so there is not even the probability that like I'm hit by a bus tomorrow and like we don't have the capacity to do it because I'm not here. Like, not even that, like, because I think that you guys now know everything that you need to know to make it work. So I'm very optimistic. I think that it will be the best thing that we have done as a team in the company.
Yeah, and I will also read through the spec, and then if there are any open questions, I will flesh it out more. And like, we definitely, if there are any things we haven't bought yet, we definitely want to catch as many possible design problems before actually hitting them during development. But yeah, it seems like it's quite straightforward and much simpler than other blockchains. And I think we could also, it can also be a big selling point if we want to get users interested in using kindelia, if we actually make it very easy to understand how everything works and document everything so that people can actually feel like they understand it, because like Ethereum itself and all these other blockchains, there are so many people who started using it, but they don't understand a lot of the internals. And there are some like YouTube videos where they just explain the surface of how the consensus algorithm works and visual things. But if we can actually make a large amount of people understand the full blockchain of kindelia, then I think it would also be a good way to drive adoption.
Yes, I agree. And I think
And
that's
yeah,
like the white
keeping it
paper will be
simple.
very small and it will be
And
very accessible.
like the Bitcoin white paper, that was also very compared to the ones that came afterwards, it was concise and elegant
Yes.
with no unnecessary stuff.